So yesterday, we graphed a pendulum swinging back and forth in its x position versus time, and we had this shape right here. And we did the spring where I compressed the spring and I released it, and it had one full period of motion there. And then we came up with an equation. We just focused on the pendulum. It was a negative cosine graph, or it is a negative cosine graph. So we have a negative sign, cosine, and A stands for the amplitude, or the maximum height there. And then we made a conversion between the angle and the angular speed or the angular frequency. So from first semester, we studied angular speed and angular frequency. And angular frequency was theta over t. So that gives us that theta, the angle, because usually in math you're used to doing like the cosine of 2 pi or the cosine of 4/3 pi. No? Yes? Okay. So we're going to convert it into a unit that tells us about the motion, because if this omega is small, or if it's large, it will affect the shape of our graph. If our angular frequency is high, it'll be squished up. If it's low, it'll be spread out. Okay. All right, so then we were in the middle of graphing the velocity time based on the position time up here when the bell rang. So our initial slope was 0. Then what's the slope through here? Is that positive, negative, or 0? It's positive. So I'm going to come up here and make a positive dot right there. I'm going to scroll back and forth here. So what about the next interesting spot right there? Positive, negative, or 0 slope? 0 slope. So then that's going to cross this time axis. There's 0 right there. Okay, so there's 1. All right, and then we've got another spot right here. Positive, negative, or 0? It's very negative there. So down here, we'd have a negative velocity. Then one last one, what's our slope right here at the end? 0. Okay, so then the shape of our graph would look like, connect the dots. Ooh. Something like that. What's that? Sine. And for those of you that are in calculus, what is the derivative of a position function? Velocity. And what's the derivative of negative a cosine omega t? Okay. So v of t is going to be some sort of sine function. I'm going to leave that blank because we're going to have a coefficient. Sine of omega t. So then this coefficient represents the amplitude in general, like from math class. And that would be like this right here. Now this is not a position graph, it's a velocity graph. So our maximum vertical value there is what kind of quantity? Okay, it's not position, it's not time, it's velocity. Okay, so the amplitude would be in terms of velocity. Okay, it needs to be velocity. Now, do you remember from first semester we had a relationship between velocity and our angular speed, or angular frequency? All right, so think about a circle. Think about an object that's going to move in a circle. And pretend that I can draw a beautiful circle. And let's let this diameter spot, I know that's not the diameter, but pretend with me. Let's let that be our starting point. And then let's graph this thing. So initially at t equals 0, the object is right there. Then at a quarter of the time it takes it to get around, it's at the top. So a quarter of the time, it's at the top. Then 2 quarters, 1/2 of the time, it's back down to the same level it was initially. Then 3/4 of the time, It gets down to a negative position. It's below the diameter now. And then for the last quarter of time, it gets back to where it started from in here. So an object moving in a circle is very sinusoidal. Okay? And we describe the speed of that particle as it goes around the circle as being r omega, where this was r. What do we call r in terms of a graph? The amplitude. Okay? So then we could write this as a omega. We'll stick it back in here, a omega. Questions so far? All right, now we've got a velocity graph. Let's make an acceleration graph. I'm going to sketch my velocity graph for you right here so we don't have to keep sliding back and forth. So our velocity looked like a sine curve. So what would my acceleration time graph look like? All right, so let's do it piece by piece so that everybody, even the non-calculus folks, can get this. So slope initially, positive, negative, or zero? Positive, so we're going to start up here. Then slope, positive, negative, or zero? Why am I doing the slope? Yeah, the acceleration is the slope of your velocity time graph. All right, what about here when it crosses the time axis? Positive, negative, or zero? Negative, so I'm down here. And then what about at the very bottom right there? Positive, negative, or zero? Zero. And then last one, positive, negative, or zero? Positive, so it's up here. And here goes our graph. Ooh, so what shape is that? It's a cosine graph. For those of you that know calculus, is that expected? Yeah, all right, so here's our cosine of omega t graph. Now we've got to figure out what this amplitude business is. What should it be measured in? If the velocity graph's amplitude is in velocity, then the acceleration's amplitude is in acceleration. Okay, so now I have a question. We have two kinds of acceleration that an object moving in a circular or repetitive motion could have. It can have tangential acceleration, meaning tangent to the circle, and it can have another acceleration, centripetal. Okay, so if this object is going to have nice repetitive motion, okay, so it's going to go nice repetitive motion and keep oscillating. Is it speeding up, slowing down, or does it have a constant velocity? It has a constant velocity, so that means the tangential velocity, this tangential velocity that we saw for earlier,